All right, thank you very much. Thank you for having me at this. So as Mike indicated, it's really impossible to overstate the influence that Tate has had on mathematics. And I want to just take one of the items from the long list of his contributions that Mike gave and expand on it. That's the theory of Barsati-Tate groups, which of course was not Tate's name for them. I'm going to follow his terminology and call them p-Divisible groups. So I would like to tell you a little bit about the notion of p-Divisible group and how it's had an impact in my own area of mathematics, which is algebraic topology. All right, so let me start from the beginning. So let's say you have an elliptic curve over a field K. And then you can look at the points of your elliptic curve over an algebraic closure of K. And those form an abelian group. And you can study the p torsion, or the p power torsion, where p is your favorite prime number. And if you look at the p to the k torsion points as k varies, they form an inverse system under multiplication by p. And you can take the inverse limit. And that inverse limit is called the Tate module of the elliptic curve. And that's naturally acted on by the Galois group of your field K. You can think of it as a representation, and representations that arise this way or from variants of this construction are very important in arithmetic. So let me give a couple of examples. So let's say you're working over the complex numbers. Then an elliptic curve is a complex torus. It looks like the complex numbers mod a lattice. And if you do this construction, you just recover the lattice back again, but p-adically completed, the lattice tensored with ZP. So in particular, it's a free ZP module of rank 2. And that's a general phenomenon as long as you avoid characteristic p. So you always get a free ZP module of rank 2. But if K has characteristic p, you always get something smaller than that. So there's two cases. If E is an ordinary elliptic curve, then instead of a lattice of rank 2, you get a lattice of rank 1. And if E is a supersingular elliptic curve, then there's no p torsion at all. You just get the zero group. And this, if you like, is one of the many definitions you can give of what it means to be a supersingular elliptic curve. So let me talk about another invariant that you could associate to an elliptic curve, which is its formal group. So if you choose a coordinate of an elliptic curve near the origin, then you can try and write down what the group structure on E looks like in terms of that coordinate. It's given by some power series in two variables. And that's called the formal group law of your elliptic curve. It's not quite well defined. It depends on a choice of local coordinate. But it's well defined up to a change of variables. If you choose a different coordinate, then you just get formal group law that's related by something like this. You conjugate by the change of variables. So you could ask what this looks like. And again, there's sort of three cases to consider. So let me assume that the field is algebraically closed. In characteristic 0, you can always choose a local coordinate so that the formal group law looks very simple. It just looks like addition. In characteristic P, you can never make it look like this. So if you're in characteristic P and you take an ordinary elliptic curve, you can do almost this well. You can get it to look like the formal group law of multiplication. So something that looks like x0 plus x1 plus an error term, which is x0 times x1. And finally, if you take a supersingular elliptic curve, then I can't write a formula for you because it would need infinitely many terms. No matter what local coordinate you choose, you can't get this to be a polynomial. It's always a power series. And that you could take to be another definition of what it means to be a supersingular elliptic curve. So let me just summarize what we've said so far. So let me assume that the characteristic of K is either 0 or p. So there's three possibilities. If you're in characteristic 0, the Tate module always has rank 2. It's interesting. The formal group law is always very simple. If you take an ordinary elliptic curve, the Tate module is a little less interesting, and the formal group law is a little more interesting. And finally, if you take a supersingular elliptic curve, the Tate module has no information at all, and the formal group law is very interesting. And so an insight that Tate and others had is that you really shouldn't consider these two invariants separately. They go together. And to formulate that more precisely, he introduced the notion of a p-divisible group. So let me give you a definition. Let's say R is a commutative ring. A p-divisible group over R is a direct system of I'll write G for the p-divisible group and G brackets p to the n for what would be the p to the n torsion on it. So each G p to the n is a finite flat commutative group scheme, which is annihilated by p to the n. And each G p to the m sits inside each of the bigger ones as the subscheme of p to the m torsion. And you have an exact sequence like this that tells you, that the map multiplication by p to the m is always a surjection from g p to the m plus n into g p to the n. So in other words, g is, every element of g is p-divisible, at least locally, for the flat topology. And usually I'll write G for the p-divisible group itself, which is the union of these G p to the n's as n varies. So let me just give an example. If you have an elliptic curve, you can look at the p to the n torsion on that elliptic curve, meaning the kernel of multiplication by p to the n. But I want to look at that not as an abelian group in the usual sense, but as a group scheme over the same ring R. And you always get a finite flat group scheme of degree p to the 2n when you do this construction. And if you look at that system as n varies, it gives you an example of a p-divisible group, a p-divisible group of an elliptic curve. So I'll write that as e p to the infinity. It's the p power torsion on your elliptic curve. OK, so what can you say about p-divisible groups in general? So let's first consider the case over a field. So one of the first things that Tate proved in his paper on p-divisible groups is that over a field, every p-divisible group fits into a canonical exact sequence where you have a subgroup which is connected and a quotient group which is étal. So here, the étal part is something that you can think of as a lattice with an action of the Galois group. And the infinitesimal part is something that you can think about in terms of formal groups. And well, unless this is not interesting unless the characteristic of k is equal to p. If k has characteristic different from p, the connected part is always trivial. And so over fields of characteristic p, if you apply this to an elliptic curve, you get the invariants that I talked about earlier. The étal part has to do with the Tate module. The infinitesimal part is the formal group of the elliptic curve. And the p-divisible group is some amalgam of the two. OK, so why would you want to consider this amalgam of the two? What does it buy for you? One thing that it buys for you is that a p-divisible group is something that behaves well in families. I gave you a definition of a p-divisible group over a ring R, which doesn't have to be a field. So for example, if I started with an elliptic curve over R, you can think of that as a family of elliptic curves parametrized by the spectrum of R. And in that family, you might see some of these elliptic curves are ordinary. Some of these elliptic curves are supersingular. And therefore, if you wanted to think about the Tate modules of those elliptic curves, as the elliptic curve vary, they don't form a nice family. The rank is changing. But the p-divisible group is something that does form a nice family. The p torsion on an elliptic curve always has degree p squared, whether the elliptic curve is supersingular or not. And another reason that you might want to consider the p-divisible groups is that when you take the formal group and the Tate module and put them together in this way, you get a very powerful invariant. And one illustration of this is the Serre-Tate theorem. So if you start with an elliptic curve, or more generally an abelian variety, over a ring where p is nilpotent, then deformations of the elliptic curve are the same as the deformations of its p-divisible group. So remembering the p-divisible group remembers, in some sense, everything about the elliptic curve up at an infinitesimal level. And here it's important that I'm talking about the p-divisible group and not just things like the Tate module and the formal group. You need to know not just those two ingredients individually, but also the extension between them, which is what the p-divisible group remembers. Okay, so before I get to what I actually want to talk about, I would just like to make two modifications of what I've been talking about so far. So far I've talked, little p has been some fixed prime number. I said, take your favorite prime number. But what if you don't have a favorite prime number? So I don't want to make you choose. So I'm going to let capital P be the set of all prime numbers. And I want to talk about a capital p-divisible group. So a capital p-divisible group is just, to specify one, you just give a little p-divisible group for every prime number p, and you add them all together. So what's an example? Well, if E is an elliptic curve, you can, for every prime number little p, look at its p-power torsion to get a little p-divisible group. But you could also just add those up as little p varies, and you get what I call a capital p-divisible group. So in this case, that would be all of the torsion on an elliptic curve where you don't specify that it's p-power torsion for any particular prime p. And the other thing that I would like to do is reformulate the definition of p-divisible group. Just eliminate the word scheme from the definition. Reformulate it in a more concrete way that's directly, that you can say directly in terms of commutative algebra. So let's say G is a capital p-divisible group over a ring R. So for every finite abelian group A, you can look at homomorphisms from A into G. And the definition tells you that those are going to be classified by a finite flat scheme over R, which I'll denote by G brackets A. And because that's finite flat over R, it's necessarily affine. It's the spectrum of a ring, which it's the coordinate ring of the scheme G sub A. So I'll write it as O sub G sub A. And I just want to observe that the construction that takes A to the coordinate ring of the A torsion on G, that's a covariant functor from the category of finite abelian groups to R algebras. And actually, if you knew that functor, then you could recover G. So for example, if you want G itself, that's the direct limit as over natural numbers n as they get more and more divisible of the spectrum of O, G, brackets, Z mod n. So it's a sort of tedious or maybe fun exercise to take the definition of p-divisible group that I gave you earlier and just translate it into this language. If you think of, if you just want to think of a p-divisible group as a functor from finite abelian groups to R algebras, well, we don't want all functors. We want ones that satisfy some axioms. So if you don't want to do that exercise, I've done it for you. So let R be a commutative ring. Here's a reformulation of what it means to be a p-divisible group. It's a functor from finite abelian groups into R algebras. So I'll, again, call the p-divisible group boldface G, but the functor is A goes to O G sub A. And what has to be true? Well, the zero group goes to the ring R. You always get a projective R module of finite rank. If you have an injective map between abelian groups, then you get a map of rings which is faithfully flat. And under the same conditions, push-outs of abelian groups go to tensor products of rings. Here, at least one of the maps from A has to be an injection. So I've given you this definition just as proof of concept. You know, I don't want to, it's not necessary to process this. I just want to say you could define a p-divisible group in this way if you wanted to. Okay, so this is all I want to say about the general notion of p-divisible group. What I would like to do with the rest of this lecture is describe for you a maybe unexpected place where p-divisible groups make an appearance in my own field, which is algebraic topology. And I would like to start not in algebraic topology, but instead with what is going to be an application of the story that I'm about to tell you. So let's go on a little digression. Oh, I'm sorry. Hold that thought. I wanted to give one more example. So here's an example of a p-divisible group that you can write down over any commutative ring. So in the language that I just described, you consider the functor from abelian groups to R algebras that A goes to R brackets A. So I apologize, I'm using the notation with a different meaning now. What I mean here is the group algebra, meaning you take a direct sum of copies of R indexed by A. So this is a functor which satisfies the axioms of the previous slide. It gives you an example of a p-divisible group. And this p-divisible group is a familiar one. I'm going to denote it by mu infinity. So that's what you get when you take the torsion points, not on an elliptic curve, but on the multiplicative group. It's the union over all n of the scheme of nth roots of unity. OK. OK, now I want to change the subject. So let's say G is a finite group. And let's say we're interested in complex representations of G. So I'm going to let rep G denote the representation ring of G. So that's just a free abelian group with one generator for every irreducible representation of G. And so one of the most basic theorems in representation theory or in character theory is a description of this ring after you tensor with the complex numbers. That is, after you tensor with the complex numbers, you can identify this with the ring of class functions from G to the complex numbers, means functions that are invariant under conjugation, functions on the set of conjugacy classes in G. And that identification is given by assigning to each representation its character. So as I was preparing this lecture, I thought it would be nice to look up the history of this theorem and try to credit whoever first proved it. So it's the 21st century, so I asked the internet. And these days, when you ask Google a question, it will very confidently give you an answer that is generated by AI. So I asked Google this question, who proved this theorem? And I actually asked it a couple of times using slightly different wording. And I got a lot of different answers. So according to Google, this was proved by Frobenius and by Schur and by Brouwer and by Kaplansky. So I'm pretty sure that last one is wrong, but who knows? Anyway, this is a very important and useful theorem in representation theory. So it has a couple of simple consequences. First, representations of G are completely determined by their character. The number of irreducible representations of G is the same as the number of conjugacy classes in G. So what I would like to do with the rest of this lecture is sketch for you a new proof of this theorem. It's not a good proof. It's a terribly inefficient proof. I'm going to take us on a long digression that's going to end here. But I think it's an interesting proof in that you learn other things from the proof as well. OK, so the proof that I'm going to give is going to take a long detour through algebraic topology. And in particular, I'm going to want to study topological K-theory. So let's say X is a compact topological space, notion introduced by Tate. And Hirzebruch is the complex K-theory of X. So K, what I'll denote by KU0 of X, this is an abelian group that you obtain in the following way. So you look at complex vector bundles on X up to isomorphism, and you observe that that has the structure of a semigroup. There's an addition law on complex vector bundles given by forming direct sums. Now that's not a group, because you can add complex vector bundles together, but you can't subtract them. So you form what's called the Grothendieck group by formally adjoining additive inverses. And that's denoted by KU0 of X. And this extends to a cohomology theory on topological spaces, meaning more generally, there's a notion of KUN of X, which I'm not going to define for you here. There's a definition when X is not compact, and there's lots of long exact sequences and so forth that make this behave like cohomology. And just as an example, let's take X to be a point. Well, a complex vector bundle on a point is just a complex vector space of finite dimension. Up to isomorphism, those are classified by their dimension, which is a natural number. the natural numbers form a semigroup, but when you formally adjoin inverses, you get the group of integers. So I actually want to consider a variant of this construction where you start with a space X with an action of a finite group G. You can give a similar definition, except instead of vector bundles, you consider G equivariant vector bundles. And then you get an invariant KU0 lower G of X, G equivariant K theory of X. And this extends also to a cohomology theory, which I'm going to denote by KU of G. It extends to what's called an equivariant cohomology theory. It means it's an invariant of a space with a G action, but except for one small place in this lecture, I'm only going to consider the case where G acts trivially on X. So let me just think of this as, it's kind of stupid, but think I'm only going to let G act trivially. And what's an example? Well, if you take the G equivariant K theory of a point, well, now equivariant vector bundles on a point are representations of G, and if you do this construction, you get the representation ring. So let's just do an example where we consider abelian groups rather than general finite groups. So if A is a finite abelian group, well, representations of A are very easy to understand. Irreducible representations are one-dimensional, and they're classified by the Pontryagin dual group. So I'll denote that by A star. That's just the group of homomorphisms from A into the complex, unit complex numbers. So that's a finite abelian group of the same size as A. And, well, what I just said translates to a statement about representation rings. The representation ring of A is just the group algebra of the Pontryagin dual group. And, well, this Pontryagin duality is involutive. I could also say representations of A star is the group algebra of A. And I just want to remind you that we've seen this construction before. I said you could encode the multiplicative p-divisible group. It's something you can do over any ring. And if you do it over the integers, that's encoded by the functor that takes an abelian group A to this group algebra Z brackets A. So I could equivalently say the multiplicative p-divisible group is encoded by the functor that takes A to the representation ring of A star. OK, so let me just elaborate on this example, but phrase it or think about the analog of this for equivariant K theory, not of a point. So let's say A is a finite abelian group now acting trivially on a space X. Well, if I want to give a equivariant vector bundle on X, that's just sort of a bundle on X where the fibers are finite dimensional representations of A. And you can take such a thing and just decompose it into its isotypics. You can think of it as a family of vector bundles on X indexed by the collection of characters A star. So let me summarize that by saying, this ring here, K0A of X, that would be the group algebra over K0 of X on the group A star. That's a statement at the level of abelian groups, but I would actually like to think of it as a statement at the level of cohomology theories. So if I take KU sub A, I'm thinking of that as a cohomology theory on topological spaces where I just let A always act trivially on the topological spaces. And that cohomology theory is like the group algebra over KU on the group A star, meaning it's a direct sum of copies of KU indexed by the characters of A. And so what I want to suggest and elaborate on in just a second is the idea, here's an example of something that you should think of as a p-divisible group, but it's now not over a commutative ring anymore. It's over a cohomology theory. And, well, similarly, I can switch the roles of A and A star, which is actually what I'm going to do in a second. So let me give a definition. So I'm going to start, let E be a commutative ring spectrum. So this is a notion in algebraic topology of a cohomology theory that has a good ring structure. So I'm not going to give a definition of this here, but a sort of theme in algebraic topology over the last few decades has been taking seriously the idea that cohomology theories with a good ring structure, they really behave like commutative rings, and you can do the kinds of things that you do with commutative rings for these objects. So what I'm going to do is an example of that. I'm going to take a notion from ordinary algebra, the notion of a p-divisible group over a ring, and I'm going to do it over a commutative ring spectrum instead of a commutative ring. So let E be a commutative ring spectrum. Definition, a p-divisible group over E is a functor from finite abelian groups into E algebras, satisfying some axioms. The axioms are exactly the same axioms I wrote down before. I just, everywhere in the previous definition, I changed the R to an E. So there's a notion of a p-divisible group over a cohomology theory. And, well, let me give an example. If you start with any commutative ring spectrum E, you can consider the construction A goes to E brackets A. And that's some incarnation of the multiplicative p-divisible group. Now it makes sense not just over any ring, but over any commutative ring spectrum. And as an example, when E is K-theory, there's another way you could describe that. That's the functor that takes A to K-theory that's equivariant with respect to the dual group of A. And that's telling you something special. I want to say something special that's going on in the case of K-theory with this p-divisible group. And to explain this, I need to tell you a little bit more about algebraic K-theory. So let G be a finite group now. Boldface G is a p-divisible group, and just regular G is going to be a finite group in this talk. And let BG be its classifying space. So that means a connected space whose fundamental group is G and which has no higher homotopy groups. So you can get something like this by taking a constructible space with a free G action and forming the quotient. And if you look at that space, BG, there's a relationship between representations of G and vector bundles on BG. The representation ring of G, as I said earlier, you can think of that as the G equivariant K-theory of a point. And that maps to the G equivariant K-theory of the universal cover of BG. And a G equivariant vector bundle on that universal cover can just be thought of as a vector bundle on BG itself. So this gives you a map from the representation ring of G to the K-theory of the classifying space. And this map is not an isomorphism. So you can think representations of G, those are like local systems on BG, whereas this has to do with general vector bundles on BG. It's some heuristic for what's going on. It's like you're forgetting a flat connection. It's not an isomorphism, but it's not far from being an isomorphism. So this is the subject of a theorem of, I think in this incarnation it's due to Atiyah, and Siegel was proved a generalization of this. But this map exhibits the K-theory of BG as a certain completion of the representation ring. Namely, you complete it with respect to its augmentation ideal. The ideal in the representation ring consisting of representations of dimension 0. So I would like to take this theorem and meditate on what it's saying in the language of p-divisible groups. I'm going to give a definition. Let G be a p-divisible group over E. E is now a commutative ring spectrum, as before. So a pre-orientation of E is something like the comparison map that we saw on the previous slide. It's something that goes from a p-divisible group is an assignment. A goes to O G sub A, which is some E algebra. And I want to map that to the E cohomology of the classifying space of the dual group A star. And I'll say that a pre-orientation is a family of maps that depends functorially on A. Both sides here are covariant functors of A. And I'll say that it's an orientation if it satisfies the conclusions of the Atiyah-Siegel theorem. That is, it always exhibits the target as a completion of the source with respect to an augmentation ideal, which is the augmentation ideal is the kernel of some map from O of G sub A to O of G of 0. And, well, you can demand this condition for all finite abelian groups A. Suffices to check it for a couple of them, just cyclic groups of prime order. And let me explain the heuristic behind this definition, that when you form this is like the coordinate ring for the scheme of maps from A into G, or the coordinate ring of the A torsion on G. And when you complete that ring with respect to its augmentation ideal, it's like you're only studying the behavior of that along the 0 section. It's like you're restricting your attention to the identity component of your p-divisible group in terms of the connected étale sequence from the beginning. So the heuristic is, this is telling you that the identity component of this p-divisible group is something fixed that depends only on E. And just as an example, I'm giving this definition as an abstraction of what happened on the previous slide. So if you look at the p-divisible group mu infinity over K theory, well, I told you that in this case, O of G sub A, that can be thought of as the A star equivariant K theory of a point. And the Atiyah-Siegel completion theorem tells you exactly that the K theory of the classifying space of the dual group is a completion of that. It's exactly saying that you have an orientation on this p-divisible group over K theory. And let me just mention, that's almost an if and only if in a certain sense. That is, if you ask, if I had a general cohomology theory E, what does it take to have an orientation of this multiplicative p-divisible group? Well, after profinite completion, it turns out E has to be an algebra over Ku. So Ku is kind of the universal example of a cohomology theory where you have a datum like this. OK, so this is a definition which has many formulations. So I've given you a formulation that makes it sound like you're demanding some abstract version of the Atiyah-Siegel completion theorem. There's another way of saying it, which is like you're demanding some abstract version of the Bott periodicity theorem. But I want to tell you another way that you can think about what this datum is or what this datum buys you. It buys you the ability to do a certain construction. And that's the construction of what I'm going to call tempered cohomology. So I'm going to start with a cohomology theory E, an oriented p-divisible group over E. And now let X be a topological space. And now I'm going to construct for you a certain cohomology theory, which I'm going to call E sub G of X. And here's the construction. I take all maps from BA into X, where A is a finite abelian group. And then I take the coordinate ring on the A star torsion in G. That's some E algebra. And I take what's called the homotopy inverse limit to get, I take the sort of appropriately defined inverse limit in the world of E algebras to get an E algebra. So I'm sweeping something under the rug here. And what I'm sweeping under the rug is that the transition maps in this inverse system have to do with maps between the different BAs. And a map of classifying spaces is not the same data as a map between the groups that they're classifying spaces of. There's some sort of base point issues there. And resolving those base point issues is exactly what the datum of an orientation allows you to do. Datum of an orientation is exactly what you need in order to make this construction functorial enough to take this inverse limit. So I don't want to elaborate on that point. We just say you can take an inverse limit like this, you get something. It's an E algebra, so it's a cohomology theory. But if you want something more concrete, you can then apply that cohomology theory to a point to get a sequence of abelian groups. And I'm going to denote those by EG upper star of X. And I'm going to call these the G-tempered cohomology groups of X. Okay, so let me tell you a little bit about the properties that this construction has. So G is an oriented p-divisible group. X is a space. First, these tempered cohomology groups map to the usual cohomology groups. So if you wanted to see the usual cohomology groups of X appear, you could give the same construction, except instead of taking an inverse limit over all abelian groups, you allowed only trivial groups. In other words, you take some inverse limit which is just indexed by the points of X. So there's always a map like this, and if X is something like a finite CW complex, so like, for example, a compact manifold or a finite simplicial complex, this map is always an isomorphism. So this definition buys you nothing if you're interested in spaces satisfying a finiteness condition like this. And the proof is essentially a simple application of a theorem of Haynes-Miller, who proved that there are no interesting maps from a classifying space of a finite group into a finite CW complex. All maps are null homotopic, so you might as well take the inverse limit, only allowing A to be the trivial group. Okay, so this is the behavior when X is a finite CW complex, but this is not the behavior in general. So let me do an example, which is kind of the motivating example. So let's go to the case where our cohomology theory is K-theory, and our p-divisible group is the multiplicative group, which I told you earlier, over K-theory that has an orientation. And now let's apply this tempered cohomology to, if we want to see something interesting, we don't want to put in a finite CW complex. Well, let's put in something almost as simple. I'll take a finite CW complex cross the classifying space of a finite group G. And then what you get out of this is the G equivariant K-theory of X. And here I'm letting G act trivially on the space X, but there's a variant of this statement for non-trivial actions of G on X, which is a little more complicated to state, so I won't state it here. So you can think of equivariant K-theory. It's a special case of this construction of tempered cohomology. And the idea of the proof is if X is a point and G is an abelian group, this is almost a tautology. It's like built into the way these invariants are defined. And the idea is you reduce to that case by a method, complex-oriented descent, which I learned from a paper of Hopkins, Kuhn, and Ravenel, which is, that paper motivated a lot of the things that I'm telling you about right now. So what else can I tell you about tempered cohomology? So let me consider a different finiteness condition that you can put on a topological space. A connected space X, we'll say it's pi finite if the homotopy groups of X are finite and they vanish in large degrees. So let me emphasize, this finiteness condition is kind of orthogonal to the condition of being a finite CW complex. A finite CW complex, which is pi finite, has to be contractible. So the kind of examples that you see here are the classifying space of a finite group is pi finite because the only homotopy group you see there is the group G. And now I want to take a stupid example of a p-divisible group. Namely, I'm going to take a constant p-divisible group associated to the discrete group Q mod Z. And, well, this always has a unique pre-orientation, and that pre-orientation is an orientation if and only if E is in characteristic 0. But anyway, you can do this construction in that case, and when you compute the G-tempered cohomology of X, you get the usual cohomology of a space, but that space is no longer X. That space is instead what's called the free loop space of X, the space of all continuous maps from a circle into X. And, well, calling this a proposition, once you unwind the definitions, this is more or less trivial. There's nothing that involved in proving this other than processing the definition. But now I want to tell you about something which is not formal, not trivial. And that's the behavior of this construction as the commutative ring spectrum E changes. So let's say you have an oriented p-divisible group over E, and then you have a map from E into some other cohomology theory E prime. Well, you can extend scalars along the map from E to E prime and get a p-divisible group over E prime, which I'll denote by G prime. And then you can ask, what's the relationship between G-tempered cohomology, which is a variant of E cohomology, and G prime tempered cohomology, which is a variant of E prime cohomology? Well, there's a comparison map. If you have any space X, you can take the G-tempered cohomology of X. That's an E algebra, so tensor over E with E prime. And that will map to the G prime tempered cohomology of X. This map is generally not an isomorphism, but if X is pi finite, then this is an isomorphism. And I want to emphasize this theorem should be surprising, because this would not be true if I was talking about ordinary E cohomology rather than tempered E cohomology. So this is the kind of behavior that you would expect if a space X was a finite CW complex. And again, finite CW complexes are almost never pi finite. And the proof of this uses the formalism of ambidextrous adjunctions, which is joint work with Mike Hopkins. OK, so now I want to get back to the application that I promised you. So if you believe everything that I've told you so far, let me deduce a classical theorem of interest. Let's suppose that we have a finite group G, and we want to study the representation ring of G tensored with the complex numbers. So my first observation is that that representation ring is the G equivariant K-theory of a point. So we're taking that and tensoring it with the complex numbers. But equivariant K-theory is a special case of tempered cohomology. So we're thinking that's tempered cohomology for the p-divisible group mu infinity applied to the classifying space BG, and then we tensored with the complex numbers. And now I want to apply the theorem from the previous slide. So the theorem from the previous slide says that tempered cohomology is something that behaves well when you extend scalars. In particular, it behaves well when you extend scalars from Ku to the complexification of Ku. So you can take Ku, tensor it with the complex numbers, and then take the tempered cohomology of BG for that commutative ring spectrum. But now, when you tensor with the complex numbers, you're in characteristic 0. So in characteristic 0, all p-divisible groups become étale. They have to do with Galois representations. C is not just a field of characteristic 0. It's a field of characteristic 0 where you have all the roots of unity. So actually, the Galois representation you see is trivial. So that p-divisible group mu infinity over the complex numbers, it's just the constant p-divisible group Q mod Z. And now I told you what happens when you take when you take tempered cohomology for Q mod Z. That is, you just get the cohomology, but not of your space, but of its free loop space, maps from a circle into BG. And because G has only one homotopy group, you can very easily describe the space of maps from a circle into BG. It looks like it has one component for every conjugacy class in G, and the component corresponding to the conjugacy class of an element G is a classifying space for a smaller finite group, which is the centralizer of that element little g. So you're computing the cohomology of this space for the cohomology theory, which is complexified K-theory. But that's a characteristic 0 cohomology theory. It doesn't see the difference between the classifying space of a finite group and a point. So this is actually the same as the cohomology of the finite set of conjugacy classes. In other words, it's identified with class functions from G to the complex numbers. OK, so that's a proof of this theorem of representation theory. But now, why am I telling you all this? What's the point of proving the theorem in this way? Well, one point is that there's a lot of other theorems that you can prove with the same method. Like I gave you an example of a theorem that you can prove using a particular example of a p-divisible group over a particular cohomology theory, which is K-theory. But there's a lot of room to vary those particular ingredients. So for example, the work I mentioned earlier of Hopkins, Kuhn, and Ravenel That's also something that you can get to pop out of this for a different choice of p-divisible group and a different choice of cohomology theory. There's work expanding on this due to Stapleton, which you can prove using the same methods. And all of these previous results were some sort of character theory for these cohomology theories, meaning they had something to do with studying finite groups or the classifying spaces of finite groups. But those are just the easiest example of pi-finite spaces. And a lot of those theorems extend to general pi-finite spaces via this method. But let me just go back to the very beginning of this lecture where we started. What's the theory of p-divisible groups for? What's the main example? I've been focusing on torsion in the multiplicative group. That's an example that you can always write down. It's kind of a boring example. It's sort of the trivial example. A more interesting example is the p-divisible group associated to an elliptic curve. And that has counterparts in homotopy theory. It has to do with the subject of what's called elliptic cohomology. And the constructions that I've outlined here are really telling you how to make sense of a theory of equivariant elliptic cohomology for finite groups and various extensions of that theory. And that's maybe what this formalism is primarily of interest for. All right, I will stop there. Thank you very much.